The AI for Good Global Summit, convened by ITU, recognizes the joint responsibility of governments, the private sector, United Nations agencies, academia and others to ensure AI reaches its full potential while preventing and mitigating harms.
And it's a moment that calls for action. And today I'm calling on each of you to use this summit to help the world to better understand what kinds of regulations, what kinds of guardrails we need to put in place right now. So together, let's make it innovative, let's make it safe, and let's make it responsible for all. Thank you very much.
Welcome to AI for Good, the leading action-oriented, global and inclusive United Nations platform on AI. Organized by ITU, in partnership with 40 UN sister organizations, and co-convened with Switzerland. The goal of AI for Good is to identify practical applications of AI to advance the United Nations Sustainable Development Goals and scale those solutions for global impact. In today's session, we're counting on you to use the live video wall feature to ask questions and post comments to help create an engaging discussion. We encourage you to stay until the end to chat, connect, ask questions, and network with our distinguished panelists and world-class AI experts in the neural network. It is now time to kick off the session and welcome our first speaker. The floor is yours.
Hello, and welcome to this session. My name is Andrea Manara from the ITU, the International Telecommunication Union. It is an honor for me to introduce the third of 5 final events for the second edition of the GeoAI ITU GeoAI Challenge. The ITU GeoAI Challenge aims to provide a platform for collaboratively addressing real-world geospatial problems by applying artificial intelligence and machine learning to advance the United Nations Sustainable Development Goals. Participation is open to any individual from one of the 193 member states of the ITU. And I wish also to inform you that ITU provides also a state-of-the-art, free-of-charge compute platform to participants of the challenge who do not have adequate access to computing resources in their institutions. Today's session deals with Landslide, susceptibility mapping. We had 201 participants enrolled in this competition, and 20 active participants submitted solutions on the Zindi platform. The top 3 teams were invited for today's session to showcase their solution, and they will be awarded during this session as a recognition for their outstanding performance. The goal of this challenge was to use machine learning to produce landslide susceptibility mapping for the Valtellina Valley in the northern part of Italy. Those maps can help local authorities to plan and implement sustainable development measures, reducing the risk of landslides and ensure the safety of community living in high-risk areas. The challenge was curated by the GeoLab, Politecnico di Milano, and contributes to the United Nations SDG 11 and 13, which focus on creating sustainable and resilient cities and combating climate change effects respectively. Now it's my pleasure to introduce the hosts of this problem statement. Vasil Jordanov, if you can switch on your camera.
Thank you and good morning.
So Vasil is a PhD candidate at the Vasilevsky National Military University in Bulgaria. He joined the GeoLab team of Politecnico di Milano as a research fellow in April 2019, where his main research interest is Earth observation and GIS in the domain of landslide, hazard and forest dynamics. Maria Brovelli is professor of GIS at the Copernicus Green Revolution for Sustainable Development at Politecnico di Milano and a member of the School of Doctoral Studies in Data Science at Roma La Sapienza. She is now also the coordinator of the Copernicus Academic Network for the Politecnico di Milano and the head of GeoLab. It is the interdepartmental lab to which 7 departments of the Politecnico are contributing. Amongst her other duties, also she's the chair of the UNGIM Academic Network, a curator of the Geospatial Series of Life for Good, and she also, I would have to say, the leading person behind the GeoAI activities in the ITU. I will now give the floor to Basil for his introduction to this competition, and afterwards we will have a 10 minutes presentation from each of the selected competitor. Basil, the floor is yours.
Thank you, Andrea. Just to share my short presentation. Okay, so thank you. Good morning, everyone. I'm Vasil Jordanov, research fellow at Politecnico di Milano, and I'm really happy to present you this challenge that we proposed for the GeoAI challenge hosted by ITU. And yeah, the topic was landslide susceptibility mapping in northern Italy. So I would briefly show you the whole idea and challenge. So I have PhD in national security and master's degree in risk mitigation. So for me, this topic in the last quite years was quite of interest, since I'm also a research fellow at the Geomatics and Earth Observation Lab at Polymi, where we have a variety of projects that we're working on urban and environmental level. So it was quite interesting for us to propose this challenge that actually was the aim was to identify patterns indicating high probability of landslides in northern Italy. So what is the problem that we wanted to solve? Actually, landslides are quite a significant hazard that are directly damaging population and infrastructure, and also they're quite big problem in Italy, especially in the northern area of Lombardy region, where the alpine massives are starting. So, and one of the solutions, or let's say the initial steps of proposing solutions, is landslide susceptibility mapping, which is a process of identifying and assessing areas that are potentially unstable and can lead to landslides according to different conditions. Naturally, AI is offering solutions also to other domains, but also in the disaster domain is quite applied now, and emerging technology that can provide great insights of data analysis and apply large machine models to different areas and to give us great insights for the landslide related problems. So with this, we propose the challenge to develop a machine learning algorithm that can detect areas and define patterns in which landslides are more probable to occur. And the area of interest is the Valtellina Valley in northern Lombardy in Italy. And the challengers were asked to develop an accurate and cost-effective model using machine learning. So this was one of the objectives, to create a landslide susceptibility mapping at high resolution, roughly at around 5 meters per pixel, where should be focused on shallow type of landslides. Another challenge is that usually the problem is also there is a zero case scenario, so where the areas with low occurrence of landslides, where the probability of happening are really low. And then as all other machine learning models, the problem is to select carefully the influencing factor or the environmental factors that can potentially trigger and predispose to landslides. And finally, to propose an accurate methodology that can be also replicable in other environments. What we provided as data sets are, let's say, local data sets that we start from environmental agency. Of course, we filtered and give some landslide information. We also gave some hypotheses for the zero case, but the participants were encouraged to incorporate other relevant data that they find, of course, open, And some of the basics that we gave as a starting point was a digital elevation model, road networks, river networks, geological information, land use, land cover, and some precipitation information. As I said, the challengers were supported and encouraged to use open data, but also to use open approaches that can foster the reproducibility and of the approach. So finally, the participants were required to submit their evaluation metrics in the online leaderboard on Zindi, their code that will be evaluated, and a report explaining the solution. And finally, to present their approach to today's challenge, final session. Of course, there are some prizes for the first 3 winners, and I want to congratulate today's presenters as they're already part of the winners. And with that, I thank you for the attention. Thank you for the ITU team for hosting and promoting the event. And I'm eager to see today's presentation. And I think we start today with Jacob. So if you can please share and start presenting. Thank you.
Okay, thank you very much. Let's share my screen. Okay, good morning, everyone. Good morning, everyone. I want to confirm if you can hear me.
We do.
Okay, thank you very much. Yeah, so I'll be talking about the Landslide Susceptibility Mapping Challenge, and my name is Jacob Ojumo. So a little bit about me. Jacob Ojumo is a data scientist with a BS in chemical engineering, skilled in data science and Python programming, and is passionate about solving health and environmental challenges with AI, that's artificial intelligence. So straight into the presentation, I'll be talking about this points in my outline: background information, the data description, feature engineering, and the rest. So straight into the background information. So of course, Landslide poses a great risk to the environment because it's more like a deformation to the head in a way. So Landslide presents a substantial risk to infrastructures and properties. And of course, the region of interest is the Valentina Valley, which is characterized by its rugged terrain. And it's really important to understand how the landslide is in this region. And of course, the whole purpose of the competition was to determine this point, and of course to help the authorities in these regions to make data-driven decisions. So the data that was given to us composed of digital terrain model, that's the DTM, and the trained data set, the road network, the river network, the geological fault zone maps, and the land use map. So the digital terrain model actually shows the elevation of these regions. Of course, as you can see, this map here is showing the digital terrain model. So the points that are dark purple shows high elevation, while the other points, which are far green, shows low elevation. So it's important for us to understand the elevation in this region so we can determine or detect the landslide. Also, we were given the training data sets, which compose of the IDs of the regions of the locations on the map, and the targets, whether landslide or not, that's zeros or one. And we also were given the road network. So it's important to understand the road activities going on in the region, because of course man-made activities or road activities could actually influence or could be a factor when determining the landslide problem. So, and also river network was one of the data that was given to us, and that's also very important because rivers could actually, there's a bit of erosion that could happen, and that could actually lead to landslide in a way. And we also have the fault zone map, so it's important to understand the faults in these regions. We were also given the land use map, so some regions are used for farming, some are used for residential activities. So these activities could also be very important when determining whether there's a landslide or not. And then we also have the meteorological maps. So of course, precipitation is important. the average precipitation is important because rainfall could actually be a big factor when it comes to landslide. It could be a very big factor. So, and then in the competition, I had to go into looking for more features because those features that were in these data sets were not enough. So I had to go into make some research about features that could be used. So I discovered I could create some more features, and these are some of the features that I created. So one of them is the topographic position index. That's the TPI. So it actually compares the elevation of each cell in a DTM to the mean elevation in that neighborhood. And then we also have the TRI. That's the topographic ruggedness index. So that also shows the elevation difference in the region. And then we also have the aspect degrees and the roughness. So of course, roughness also shows it quantifies the irregularity in the elevation in that area. So it's very important. Also, E-shade also. So it's very important to understand this features. So, and these features were actually obtained from the GeoAI library in Python. So I got them out from the GeoAI library, and I also created the distance to the nearest river, distance to the nearest fault, and distance to the nearest road, because I realized that they're also very important. Not just knowing where the river is, but it's also important to understand the distance between a particular location and the nearest river, because like I said, rivers could actually erosions from rivers could cause erosion, so it could have a little bit of effect on the landslide, of creating a landslide, and then the faults and then the road management activities could also have an influence. So this maps show the TPI and TRI. So I'm just showing us two out of several other features that I created. So this topographic TPI, rather, it's showing from a range of negative 0.04 to 0.04. So this TPI was actually important in the modeling, and then the TRI also, which is very obvious that it ranges from about zero to about 2 point something. So that's so where it's zero. So where it's zero is showing that there's a little bit of ruggedness. And I realized that when doing my analysis, I realized that, okay, these points that are sort of really obvious that there's a line going past them, it shows that there's a high elevation there, that I feel like they are very rocky. I mean, they are mountainous regions in that particular Palestinian valley. So that was my conclusion about that. So, and then I went on to create histograms of these features that I also created: the distance to the nearest fault zone, distance to the nearest river, and distance to the nearest road. So distance to the nearest fault zone, the first one over here, it's the histogram is showing that, so all of them are actually right skewed. We have more data on the left, right? We have more data on the left. So it's showing that most of the regions have fault zones that are like the fault zones are really close, like nearest fault zone is very close. That's also what it means. And then the same thing goes for the river also. Most regions are close to the river, and some regions are very far from the river, like 8,000 meters, or I'm not sure if it's 8,000 meters or kilometers there. And then the nearest road, that's also an important feature. So I realized that there's also imbalance in the data set that was given to us. So this table shows the distribution. So for the 0 means a non-landslide, and of course 1 means landslide. So for the landslide positions of regions, we have about 10,403, and then the non-landslide, that's like 1,657. That's showing like a 86 to 14% ratio, percentage. So that's a huge difference. That's a huge difference. So I decided to use the random oversampler. I tested several other sampling techniques, but I had to use the random oversampler in the end. So so that was to increase the regions that are not, I mean, the non-landslide, which is having a low presence here, that's the 0. I increased this so it can match up with the landslide. So it's just like creating new data points so it can match up. So, and then I went on to do the modeling and the evaluation. So for the modeling, I used the CatBoost LGBM XGBoost is gradient boosting classifier also. But first of all, I had to take a K-fold of all of them, cross-validation of all of them, for each of them. So I think I took about 5 votes for each of these models, and at the end of the day, I found the median of whether it's landslide or not. So that gave me this. So that gave me these results. So for the cap boost, I had about 0.9773 for the mean accuracy, and this table shows several other metrics. That's the mean precision, mean recall, mean F1 score. So for the mean accuracy, XG boost was the highest. That's about 0.9847. Okay, so LGBM was the highest, actually, 0.9863. So that's a mistake there. So LGBM performed well for the mean accuracy, and for the mean precision, LGBM also performed greatly. And for the mean recall, this gradient did better. For the mean F1 score, LGBM performed greatly again, and then for the last one too, so LGBM performed greatly again. So overall, I think LGBM was the man for the job here. So then I went on to look at the data distribution after I had created the models, after I had made the predictions. So I realized that there's almost an equal balance between the regions. Between the regions that have no landslide and regions that have landslide, as opposed to the training data that was given to us, because the training data, there was a lot of imbalance. As we saw earlier, that's like 86 to 14%. So 86% was having landslide and 14% non-landslide. So that's like a huge difference. So I expected that after modeling, but that was not the case. So as you can see here, there's a close relationship, close distance is not so much. So for the cat boost classifier, points that had no landslide was about 52.4%, while the ones that had landslide was 47.6%. So there's a close balance there. So, and then for the LGBM, that's 50.3 and 49.7, and then the other ones too also had differences. So, but then I had to conclude with the final submission by using 51.7% as, when I did the mean of everything, the mean results. So the mean result of all of this, so that's what I have in my final submission. So at the end of the day, 20,661 points had no landslide, while 19,239 had landslide, and in a ratio of 51.7 to 48.3 in terms of percentage there. And at the end of the day, this is the distribution of the landslide. So where the points that are blue shows that there were no landslides, and points that are red shows that there are landslides in those regions. Yeah. Thank you.
Thank you, Jacob, for the interesting presentation. I think next can present Marcos, if you can share. Thank
you. Okay. So just to check, can everyone hear me and see my screen?
Yes, we do.
Okay, awesome. So, hi everyone, I'm Marcos. Today I'm going to be talking about my solution to the Landslide Susceptibility Challenge. So, a little bit about me. So I just started my master's in data science at the University of Padova. Literally just started it. I have a bachelor in physics at the Federal University of Rio Grande do Sul in Brazil. I previously worked as a data scientist for BTG Pactual. I have research experience applying AI to astronomy, and my main interest in AI is actually the applications of it to science. So this competition kind of fits with my goals of exploring what is possible with AI. So getting into the competition, quick talk about the motivation. Landslides are a very big threat to both human life, infrastructure, the economy of a place. If there was a way for us to be able to map them and predict the zones where they are more probable to happen, it would be very useful for authorities to ensure the safety of the communities living in those areas. So this really motivates the creation of a model that uses geographic data to be able to, map the zones that are more susceptible to landslides. So getting straight into the meat of my submission, start of the data. I used only the data that was provided by the organizers. And for both the purposes of my submission and the purposes of this presentation, I'm going to be dividing them in two categories, which are the geodata frames, which is vector data, the GIS data, and the rasters, which is kind of like image data with like geographical coordinates. Initially, a very important first point, the training data was in multi-polygon format, while the test data was in point format. And to solve this, I took basically the easiest solution, which was to consider the centroids of each multi-polygon of the training data as the points. So you can see this is a map of the training data set. Zeros are zones with no landslides, and 1 are zones with landslides. And you can see that after we transform these multi-polygons into points, we get a very big decrease when it comes to the area of basically the proportion of the two areas between no landslides and landslides. So this is already a point that is we could probably improve on. So for instance, if we consider this area on the west over here, there are a ton of points in this area, and it turns into just 1 point. So, but yeah, I just used the centroids. So getting into the data processing, I did a bit of data cleaning. I removed irrelevant and redundant features from the data frames, the geodata frames, so the vector data. Irrelevant features are features that are basically only one value for all of the points in the geodata frame. And redundant features, I consider them as being basically columns that have different names, but they convey the same meaning. So we have this example over here, like this column on the top, it's the same thing as this column on the bottom. The only difference is that one has numerical data and the other has text data, which in the end for our model doesn't really make a difference. So yeah, this is just a bit of data cleaning that allowed me to decrease the number of columns I had to deal with. So buffering. This is the main idea that I used for my solution to the challenge. And I gotta say, my solution to the challenge is that it does not come from a geoengineering point of view. It comes more from a data point of view. So basically, I didn't really use any kind of features related to the geography. I just looked at the data and used very basic statistics. So buffering played a really big role. So we converted our training data points to points. And if we want to calculate stuff related to the overlaps, the intersects between these data points and the other features such as rivers, roads, geological faults, the points are just a point. So the other geometries are not going to be intersecting with our new point geometry. And to solve this, I used buffering to create an area around each point. And then I looked at the overlay between this buffer area and the geodata frame data. And in my case, I considered 4 buffer radii for my data processing and feature engineering step, which are the following radii in meters. So just to visualize what is happening here, this is the land use vector data. Our data point is this little black point with the white outline, and the buffer area is this gray circle. And the thing I'm doing is that, first off, I'm creating this buffer area around the point. So I'm expanding the view that I have. And I'm considering just the parts of this geometry that intersects with my buffer area that are inside this grayish circle. So for instance, if we look at this blue area over here, I'm just considering this very small section instead of considering the whole blue section. So what I did is that I basically created features from all of the geometries, all of the specific categories for each geometry that intersect with this buffer area. So for instance, I have this column over here, which is river, from the river vector data. And then I look at the nome corpo hídrico feature from the river vector data. And I basically look at the category of the nome corpo hídrico feature from the river data that intersects with my buffer area. So it's also important to note that I also calculate the distance between our initial point and the geometries that end up intersecting with the buffer area. So we can see that there are a lot of like nada numbers, because there are a lot of new intersections. So for instance, this ID has no intersection with a road within the 100-meter buffer radius. So yeah, it's basically a very raw way of getting features. So when it comes to the feature engineering, the first thing I did is I removed all of these nans, and I defined functions that calculate different features. And I created very generic functions that can be applied to any kind of column. So I consider the density of a categorical column by a numerical column, the proportions of a sum of numerical values in relation to a sum of other numerical values, and the proportion of one category in relation to the total number of categories. And lastly, some statistics of the distance measures between our point and all of the geometries. So it's stuff that has some geographical meaning, but it's very much like data, very basic statistics that we're considering here.
1 minute.
Sorry?
1 minute.
Okay. Yeah, this leaves us with a very big data frame. And I did basically the same thing with the rasters. I consider just statistics. The only exception is for the terrain rasters, where I did some very basic feature engineering. And we are left with a ton of features, like 1,700 features, which is a lot. When it comes to the model development, I use the light GBM and perform a hyperparameter search. And these are the results from the best model on the training set. And for the inference, I basically use the light GBM to get probabilities and created a susceptibility map. This is considering the test data set, so we can see this is the reason like why there are a few gaps over here. It's not like perfectly homogeneous points. And yeah, just like some next steps, how this could be improved upon. I think initially find a better way to convert the multi-polygon to point data. So maybe like for big areas, we could take a lot of points instead of just the centroid. Reduce the number of features. I have a lot of features. Most of them are very sparse, lots of zeros. This could be done with the feature importance function of LightGBM. Calculate susceptibility maps with finer resolutions, so we get more points. And also implement more meaningful features derived from area knowledge, which is something that I did not do. I use very general statistics features. So yeah, that's it for me. Thank you for listening to my presentation.
Thank you, Marcos, for the interesting presentation and for the solution. And I think now the last one to present is Muhammad. If you can share your presentation. Thank you.
Hello, everyone. Can you see me? And can you hear me?
Yes, we can. Yes, we can.
Yeah. So my name is Muhammad Luai, and I am a data scientist.
Mohammed,
Yes.
Could you share your screen?
Okay. Yeah. Can you see my screen now?
I can.
Yes.
If you could go into full presentation mode.
Well, this is a notebook. This is a Jupyter notebook.
Okay.
So I'm a data scientist at Zindi, and I had just joined Zindi when I got to know about this competition. So I looked at the effects that the landslides are causing in Italy, and it had me intrigued. So this is the area of interest, and so this is the data sets that we were given. There was a digital terrain model, a training data set, and we had also the road networks, which so we had the road networks, the river networks, geological fault zones, and the land use land cover, as well as meteorological data, which included the yearly averaged hour precipitation and the 90th percentile of the hour precipitation. So my solution was actually very simple. So I just used the data that was given to engineer features. So based on the digital terrain model and the geometry points, I extracted the DTM mean of that specific point. And then based on the rainfall, I extracted the average precipitation for 2020, the mean. And then I also extracted the 90th percentile precipitation mean, because we know that whenever there is rainfall, land is more susceptible to, so there is more susceptibility to landslides when it rains. So these are useful features. And then the distance to a fault. So we expect that the nearer we are to a fault, the more likely we would have landslides. Similarly, rivers are likely to cause fault zones and weak zones. So this was also an important feature. And then also the distance to road, we expect that the closer we are to a road, the more susceptible our land would be to landslides. And then the elevation at that specific point. So the places that are higher have higher susceptibility to landslides than the places that are lower. And then we also have the X and Y, which are the latitude and longitude of that specific place, as well as the slope and the aspect. So I didn't do much of feature engineering. Just based on these features, I trained a random forest model. Then I had an accuracy of 96%, a precision of 88% on the falls class, and 97% on the landslide class. So when I submitted this on Zindi, these were the results that I got. So the public score was 94.725%. So as you can see, there's not much of overfitting, and because this is like 95% and this is like 96%. So finally, there's the TIFF file that displays the areas that have faults and the areas. So based on this legend, so one is very low susceptibility to landslides, and so 2 is a low susceptibility, 3 is moderate, 4 is high, and 5 is very high. So what I could have done different is perhaps I could have done more feature engineering and improved the model even much further. I could have come up with more features and come up with an even better model. So yeah, thank you. That's my presentation.
Thank you, Muhammad. Oh, okay, so we saw the presentations, and I think we can proceed to the final award ceremony.
So I will share my screen in such a way that when you announce the rank, I will show the certificate. Okay.
And
Okay.
we can ask also the candidates to
Yes.
switch on their camera.
Please, good idea, Maria.
Okay, they're showing. Okay, again, to take all the participants for submitting their solutions and for the presentations. Quite the decision, I would say, with the ranking. And the solutions were good. We were considering the solutions, the codes, the documentation, and also the maps produced. So I would start with the awarded third place, which after some verification, it is Muhammad. Congrats. And for the second place is Jacob. And the winner is Marcos. Congratulations to all three of you.
Yes. Congratulations to all for a very nice involvement in the competition and very nice work, reports, and presentation in this event. I thank you very much. So maybe now we can go to the last part of this event. So the last part is about an outlook for next year competition. I would like to begin by maybe asking all the participants which is your feedback about the competition, if there is something that we can improve, anything that comes to your mind. If there is no feedback on that, maybe I can ask also Maria and Basil. I want to thank you very much for your involvement in the competition. This year your GeoLab has submitted 2 problems. The first one on air pollution, which was debated on Monday. And so we are really happy with your involvement, and we would like to know which is your experience, which is your feedback out of this event, and if you will think about participating again, maybe next year, if you have some ideas, any feedback.
Yeah, thank you, Andrea. I will start more in general, and then I leave the word to Basil with respect to the specific challenge. I believe that these events are important, specifically for young people like Marcos, Muhammad, and Jacob, because this gives you visibility. So it's first of all, you are helping in finding solutions that are relevant. Please pay attention to the fact that this event is organized by ITU, which is one of the agencies of United Nations. So in doing what you did, what you have contributed, you are contributing in any case to United Nations for addressing better the Sustainable Development Goals, which is the framework that United Nations decided to adopt to improve the quality of the life in our world. So first of all, you are doing something which is relevant for everyone. And the second, for sure, you are improving also your visibility, because being the winner of the challenge means that you are exposed in YouTube and in general with respect to what you did. And with respect to that, I want also to offer you one more possibility, because there is a journal of ITU, and this journal of ITU has a special issue which is related to GeoAI. So if you are interested, I'm proposing the four of you, so I mean Vasil and the three competitors who got the best results, because we had also other competitors, but you are the winners. My proposal is that you prepare a paper together in such a way to be published on this journal, where you can communicate and present the solutions that you proposed, but also where is the code that you are using, in such a way to make what you did replicable by everyone, because this is the meaning of this challenge: providing an open solution that can be reused everywhere in the world by all people in the need. And after say that, which is very general, I leave the word to Vasil for commenting more specifically this specific challenge.
Thank you, Maria. Now, I would like to thank again to the participants that submitted their solutions and report. Firstly, that they compiled with the requirements, what we asked them to submit. And the solutions were really interesting. And for me, what, let's say, really made me pay attention now during the presentation, that all of you, I think three, mentioned that there were the points of improvement. So one thing is that you don't find the solution as close. There is point always to improve, which as a research problem, as a landslide susceptibility mapping, you cannot close it that easy. So I really interested that can be find another solution, other improvements. Yeah, thank you again. Thank you. And I would be happy if you're interested in participating in the initiative proposed from Maria. Thank you.
Thank you very much, Vasil, and thank you very much, Maria, for having hosted this competition. I want to thank again to all the competitors who have presented in this final, to Muhammad, to Jacob, and to Marcos, and I congratulate you again on your achievement. And then I thank you also all the other participants of this competition. And I also wish to remind you that this session has been recorded and is available on YouTube and on the neural network. And with all the other GeoAI events which we have been recorded in these last few years on the competition side, but also on the GeoAI discovery webinars that have been curated by Maria. We are starting having an impressive amount of material for GeoAI. And with this, I thank you very much and I wish you a nice continuation of your day. Bye.
Thank you, Andrea, and the ITU team.
Thank you again. Bye-bye. Bye.
Thank you, everyone, and congratulations for your solution. Keep in touch for the next events.
Thank you.
Thank you for participating in today's AI for Good session. We hope you've learned something new, innovative, engaging in today's event. We now encourage you to continue the conversation on the live video wall in the neural network. You can ask questions, like and comment, links, complete the poll, and with interesting profile, or speak on one using chat and video. We invite you to explore the log, try matching quiz, visit the virtual exhibit, post called Deep, and build your personalized AI for Good program. Let's shape the future of AI for Good.
For good recognizes the right responsibility of governments, the private sector, nation agencies, academia, and others to ensure AI reaches its full potential.
At the moment that calls for action. Today I'm calling on each of you to use this summit to help the world to better understand what kinds of regulations, kinds of guard we need to put in place right now. So together, let's make it innovative, let's make it safe, let's make it responsible for all. Thank you very much.